Welcome back to fall semester. Hope everyone had a great summer. This will be our first APS department colloquium at our new time and in this room in person. Are you? All right. Okay. So as has become recent tradition, today we'll be doing a round robin colloquium. So everyone who signed up in advance, note the slides were frozen 10 minutes ago. Yes, gotcha. Everyone who signed up as of 10 minutes ago will come down and have 1 minute. The timer, oh, we'll go over the ground rules. So we'll do that. Okay. Oh, this doesn't advance the slide. That's very exciting. I can click. Okay, great. So this is me. Sorry, I'm Jason Dexter explaining the ground rules. So we'll have 1 minute each. And please know roughly where you are in the slide deck, where you signed up, because the timer will start when we advance the slide, not when you come down here. Okay. Crucial difference.
So queue up.
Yeah, well, that's how, that is one way to do it. Yeah, you can queue up if you like. Okay, any other important ground rules? Yeah, we want to get to know each other and what we work on, but we also need to keep it brief because there were 40 slides in the slide deck. Okay.
Speaking, please use the microphone or you will not be recorded. There. Wordless speech, but recorded.
Doesn't sound that bad. Okay, shall we get started? Anything else before we get started? Any who's first? They're not down here yet. Okay, here we go. I need to have the time. There's some logistics. Okay, here we go.
That's also me. That's okay. I'll be less than a minute. Hi, everybody. I'm Meredith McGregor. I am one of the assistant professors in the department. Hi, new grad students in the back that I haven't all met yet. You're going to hear a lot of me next week because I'm giving the colloquium. So to avoid repeating everything, I thought I'd highlight what I've been doing over the summer, which is leading the development of a new probe mission concept for NASA. NASA has a call out for probes, which are $1 billion spacecraft right now, and in the far infrared and X-ray. So I'm the deputy PI for FIRST, which is the Far Infrared Spectroscopic Survey Telescope, which is a mission specifically dedicated to high resolution spectroscopy in the far IR. It's super cool. Happy to talk about it. That's everything I have to say.
Our department chair does not get extra time. Over.
Good afternoon. My name is Nils Halverson. I'm a professor in the department chair. This is a lovely picture of the South Pole telescope located at the South Pole, and that picture was taken during the winter. I'm working on that project and other projects to explore the cosmic microwave background, which promises to reveal some very interesting information about the epoch of inflation and also the mass of the neutrinos. So if you're interested in hearing about those or other South Pole Telescope or other projects I'm working on, stop by my office. Thank you.
Hello, I'm Kevin Reardon. I'm a scientist at the National Solar Observatory, and I study the sun in what I like to call maddening detail. So up in the upper left, there's the photosphere of the sun, and you see the convective cells pushing around the little kilogauss magnetic flux tubes. And that's the boring part of the sun for me. I like the chromosphere, where the magnetic field and the plasmas really start to duke it out. They have sort of equal pressures, and so they can do all kinds of neat things like reconnection and conversion into magnetic waves. And the other thing I'm working on now is some expeditions and some future eclipses to measure the electron temperature in the corona. So all through the atmosphere. Thanks.
Lucky that I'm very bad at using this phone timer.
Hi, I'm Kevin France. I forgot where I was in the slide deck. So I'm a associate professor here in APS. My group studies stars and planets and how they get along, both from observations from the ground and space. And we also build our own experiments. So we spent the summer in Australia launching a sounding rocket to observe the far and extreme UV spectrum of alpha Cen A and B. We got the cute CubeSat mission, which is actually struggling today, but it was doing great last week. So if you're interested in student hands-on hardware or stars and planets, please come talk to me later. Thanks.
Oh, I think David said he couldn't come, so we'll study the slide in silence for 1 minute. Please. All right, David Malaspina, take it away.
Thank you. Okay, so I'll represent for David, just since I'm a fellow assistant professor at LASP. He studies space plasmas ranging from sun and solar wind into Earth's magnetosphere and ionosphere. He has a few different experiments going on, a CubeSat called Canvas, a sounding rocket called Cousin coming up or under development currently. I think an instrument going to the moon, Lucy, and then lots of data to pour through from larger NASA missions like Solar Probe and MMS and Van Allen probes. So I'd say reach out to him directly if you want to hear more about any of that. And I think perfect. So my name's Lauren Blum. Welcome again. My research is somewhat similar to David, so studying the interaction between the sun, the solar wind, and magnetized planets, particularly Earth's magnetosphere. I focused a lot on energetic particles in the magnetosphere, so in Earth's radiation belts and plasma wave interactions with these particles. I also have some hardware projects going on, some instruments under development currently to measure energetic particles, and a CubeSat that is ready to be launched, as well as one that is hopefully going to be funded soon. So at a few different stages. And then coming up this March, actually, we have a balloon campaign from Finland that will study changes in Earth's atmosphere and actually measure changes in ozone driven by some of these magnetospheric particles. And so if any grad students or undergrads want to get involved in any of these projects, feel free to reach out to me. Thanks.
Hey guys, my name is Mikayla Huffman. I'm a first year here. I'll be working with Dave over there in the corner. But my undergrad work is predominantly focused on impact physics. I've done a bunch of other stuff, but this is the most recent thing I was working on at SPIRI this summer, is tertiary impact cratering on our moon. So you may have heard of secondary impact cratering. You can see here's Wallace. It's unnamed. I'm just calling it that. That's our primary. You can see some of these secondaries over here. Nice grommet and cheese. And then we're actually looking at secondaries of those secondaries in the yellow ellipses up there. This is pretty new. They're pretty small. The boulders you see there are about the size of a Mini Cooper, and they are pretty slow, down to 5 meters per second for that bouncing out velocity. So yeah, I work on small and big craters. Thank you.
Hello, everyone. I am assistant professor here, Maria Kazachenko, and I try to understand solar magnetism on the surface and above. Specifically in the quiet sun on the left, you see a magnetogram from Solar Dynamics Observatory, different colors, different directions of magnetic field. So we're trying to understand how solar eruptions happen and also small scale magnetism. Besides that, we do some outreach in English and Spanish, and we're preparing for upcoming solar eclipses. We're getting ready for the data from the Dicas telescope. And if you have any interest in solar eruption simulations, observations, please drop me an email.
Hi, I'm Benoit Tremblay. I'm a postdoc working with Masha Kazachenko. And my research focuses on the application of machine learning in solar physics. And here are 2 examples of that. So on the left, for example, we learned from state-of-the-art numerical simulations of the sun to make relationships between the quantities that satellites and telescopes can measure and quantities that we cannot measure. And then once you've learned from the simulations, you can apply to the observations and get an estimate of what you can't measure. Like in this case, we're going from white light images to the plasma motions. And on the right, it's a different project. Here we learn from the images in EUV that were captured by 3 different satellites orbiting around the sun. And we reconstructed a 3D sun from it. And our neural network basically acts as a virtual observatory that we can place anywhere in the solar system and get never before seen views of the sun. Thank you.
Okay, great. This is me. I am Jason Dexter. I'm an assistant professor here, and I study accretion onto black holes on the smallest scales, in particular using spatially resolved observations like shown in the Event Horizon Telescope image there. And some of the things we've learned are that, at least in the galactic center and M87, we think that magnetic fields near the event horizons of black holes are actually very strong, and they can influence how the gas falls in and push it around. And we're trying to do calculations now of also going to higher luminosity and other systems to understand how accretion physics might work, especially in the presence of strong magnetic fields. And a lot of this work is computational. We're also involved in the Event Horizon Telescope and gravity experiments.
Hi, everyone. I'm Tatsuya. I'm a fourth-year grad student at APS, and I work with Anne-Marie Madigan on stellar dynamics around supermassive black holes, so the motion of stars around supermassive black holes. And specifically, I work on the formation of this kind of lopsided stellar disk that you see on the right-hand side. So in a letter that I published last year, I went from the circular disk to this lopsided disk over here. And now I'm working on kind of more general configurations of what you can get, specifically from what's called gravitational recoil kick. So this is when two supermassive black holes merge together and they emit gravitational waves, and there's a recoil kick on the merged remnant. And so I showed that you can form this lopsided disk over here through that. And so now I'm working on evolution of these systems and also tidal disruption events, which are when stars get ripped apart in this kind of system. Yeah, thank you.
Hey everyone, I'm Paul Hayne. I'm a fifth-year faculty member here in the department and third-year dad also. So I study the surfaces and atmospheres of terrestrial planets and moons, a few of which are shown here, using observations from spacecraft missions, including Cassini, the Mars Reconnaissance Orbiter, and Dawn mission for Titan, Mars, and Ceres. And I use mainly infrared remote sensing and including thermal infrared and near infrared spectroscopy, along with computational models to understand the distribution and behavior of volatiles and ices in the solar system and how those interact between the surfaces and atmospheres of these planetary bodies. And that's about all I got. Thanks.
Hey, I'm Hannelore Gerling Dunsmore. I'm a fourth-year graduate student working with Mitch Biegelman on quasar fueling, supermassive black hole formation, and supermassive black hole growth. I'm using this because otherwise I will ramble. My primary work is investigating how magnetic processes, such as the magnetorotational instability, and honestly, entirely the magnetorotational instability, it can suppress the gravitational instability in quasar accretion disks, thus preventing catastrophic fragmentation of the disk, which allows it to do all the things that we see it do. Well, that we see coming from there. And my secondary work is with the SMOG collaboration, which is based at the Center for Computational Astrophysics at the Flatiron Institute in New York City, studying the coevolution of rapidly accreting supermassive black hole seeds and their host galaxies, and also studying the environmental properties required to enable that rapid accretion.
Both? Hi, I'm Anne-Marie Madigan. I've not prepared anything. I am an assistant professor with tenure. Thank you. That was so, I'm not saying anything useful, am I? Okay, so I work on gravitational dynamics. This includes galactic dynamics. In particular, a project I'm really excited about right now is when we take galaxies with stellar bars and we flip the orientation of the stellar bar using dark matter for fun. There's no reason to do it. But I also work on the outer solar system in particular. There is no planet 9, as you've all heard me say. And then particularly with Tatsuya, working on tidal disruption events, stars that get too close to supermassive black holes and get ripped apart. And that's fantastic. Thanks.
Hello. Okay, this is working. So I'm Margaret Landis. I'm a LASP researcher, and I used to be Paul Hayne's postdoc, and now I mostly work with Paul. So here are some varieties of the icy craters I work on in the solar system. This is Oxo crater on Ceres. This is invisible, not near infrared, so you can't see all the water ice absorptions inside that crater. So one of the things I do is look at the history of volatiles in series. This is a high-rise image. So this is a 25 centimeter per pixel camera on Mars Reconnaissance Orbiter. That image of a crater into the southern ice sheet was taken 2 weeks ago. It's not icy, it's weird. And then finally, I look at the lunar poles using diviner data to understand where volatiles could be stable. So if we detect them or not detect them in the future, we'll figure out how to interpret it. And somewhere on this crater's rim is a potential Artemis landing site for humans. So that's really cool. That's a minute.
Okay, hello, I'm Dave from the corner. I'm an associate professor in APS, and my research home is in LASP. My research lies at the boundaries between planetary science, heliophysics, and lately also reaching small tendrils into exoplanet science and even astrobiology. The kind of techniques that I use, I'm trained as an observer, but I'm one of the few astronomers that does not use light. I use particle and field measurements, which requires sending a spacecraft to your destination. And these days, I'm maybe 2/3 observations and 1/3 simulation and modeling. The picture here depicts the question that gets me out of bed in the morning currently, which can be summarized in 6 words. Do habitable worlds require magnetic fields? And the connection there is through escape of the atmosphere to space.
Hi, so I'm Nisha Schneff. I'm a postdoc with Dave Brain, and the segue there is I'm also interested in whether magnetic fields are necessary for a planet to be habitable. I'm interested in a variety of planetary magnetic field problems. So I also look at some terrestrial problems like, can we use magnetic signals to understand and better like improve warning systems for tsunamis and other hazards like that? And then also with like icy moons, can we use the tidal signals from the ocean's magnetic fields to study the interiors of these moons? So these are the different things I do, and my home is at LASP. Thanks.
This is fine. It's fine. You're doing great.
Thank you. My name is Yuta Notsu, and I'm a postdoc working with Adam Kowalski, and I'm basically in a LASP. And my research interest in stellar flares using various instruments, including Apache Point Observatory and TESS satellite and some X-ray UV telescopes. And in a few years, we also working on observational candidates of stellar coronal mass ejections, and it's becoming a very interesting topic. So, and also important for effects on planets. So, if we have interested, please let's have our discussions. Okay, thank you.
All right, hi, I'm Steve Cranmer. I'm an associate professor in APS. I study the sun and other stars. In recent years, I've been trying to take more of a sort of a systems approach to the whole system, from the tiny little features at the surface of the sun, the loopy magnetic structures in this low solar corona, and then the way they expand all the way out into the heliosphere, the rest of the solar system, and form, solar streams that can impact the Earth and cause space weather. So yeah, I think following on from Dave's percentage, I think I'm sort of, 75% theorist and 25%, somebody who looks at observational data. I've got some missions along the bottom here, everything from sort of the very focused stuff at the sun from DKIST to some old and some new missions and some currently flying missions studying all these different layers of the sun. Yeah, lots of different ideas, trying to stitch it all together and understand the whole system.
Hello, I'm Andrew Hamilton. I'm a professor in APS and GILA. If there is a theory of everything, then spinors, particles of spin half, are probably at the heart of it. Just look around. All known matter, quarks and leptons, is made of spinors, and all known forces arise from symmetries of spinors. The standard model has been known since the 1970s to fit nicely in the grand unified group spin 10. It is obvious to ask whether spin 10 and the Lorentz group spin 3.1 of relativity unify non-trivially. Indeed, they do in spin 11.1. A spinner in any number of dimensions is described by a bit code. In 11 plus 1 equals 12 dimensions, there are 12 over 2 equals 6 bits, each of which can point either up or down. This chart shows the 2 to the 6 equals 64 fermions of a generation. Besides the 5 bits of the standard model, there is a 6th bit, the t-bit or time bit. Flipping the t-bit flips a fermion to an antifermion. Nice. Thank you.
Hi, everyone. I'm Seth Hornstein, teaching associate professor in the department, which means I spend most of my time thinking about our classes. In particular, I think about how do we teach our non-major introductory astronomy courses. I'm also the undergraduate associate chair. So if you have questions about the department or program undergraduate-wise, you can come talk to me. But what gets me out of bed is not only my love of teaching, but also playing with telescopes. So my other hat is I'm the director of Summers Bowers Observatory, where we have 2 20-inch telescopes and our 24-inch telescope. Most of the grad students and faculty know that you can volunteer and get involved in the observatory, but for the postdocs, we'd love to have you involved as well. So if you want to get trained on the telescopes and help out with open houses, we'd love to have you. So come talk to me if you'd like to play with telescopes. Thanks.
Thanks, Jason. I'm Larry Esposito. I've been at LASP since 1977. I'm interested in the structure and dynamics of Saturn's rings and what we can infer about the origins of planetary rings and maybe protoplanetary disks. And this multiple image, you start at the bottom, which is a picture of Saturn's rings from the Cassini camera, and then a different way of looking at the rings as we watch a star pass behind them. And you can see there's very good agreement between the picture that we see and the opacity of the rings, which is plotted there. The advantage is that the occultations have 100 times the spatial resolution of the pictures, the best pictures from the Cassini spacecraft. And to see this, you can look at up in the top, those spikes there in the A ring of Saturn are actually density waves, which are unresolved, which in some of the best images are resolved in the upper right. And our task is to go even below the capability to exceed the resolution to look at meter scale structures in the rings, not by looking at the starlight intensity, but looking at the variance, the kurtosis, and the skewness of the statistics. And we're able to see structures, identify structures in the rings that are a few meters across. And maybe they're the structure of self-gravity wakes originally proposed by Alar Tumri, that clumps form in the rings of these rectangular structures, and maybe also in protoplanetary disks. Thanks.
Hi, I'm Matt Kelcher. I'm a new graduate student coming to you via Wisconsin, Bucky Badger there. My current interests are in exoplanets and planet formation, though I have no project at the moment. So if anybody has something, let me know. In the past, I've worked on substructures and compact protoplanetary disks. I've worked on lensed submillimeter galaxies. And I've also, here at NSO, I did stuff with the solar spectra. So thank you.
Hi, I'm Neil Bassett. I'm a grad student and I work with Professor Jack Burns and also other grad students, Joshua Hibbard and Johnny DeRigo Jones. So we do observational cosmology, and specifically we use the highly redshifted hyperfine transition of hydrogen, which can tell us about the early periods of the universe, including the dark ages, cosmic dawn, and the epoch of reionization. The dark ages is particularly interesting because there's none of that pesky astrophysics that we all hate. It's really just pure cosmology. And this is a really exciting time period for our group in the field. We're involved with 2 different missions that have been selected for flight through NASA's Commercial Lunar Payload Services program. So the first is called Rolls's, which is going to the near side within the next 6 months. And then later in 2025, Lucy Knight is going to the far side and is going to produce really the most pristine data set we have so far from the radio quiet far side. Thanks.
G'day, John Keller here, teaching professor and director of Fisk Planetarium. If you haven't been to Fisk, come. We make films, Jack Burns' Forward to the Moon, things about the Mosaic mission in the Arctic, a musical about Voyagers, cosmic mashups, Julie Comerford's film coming out in November, and then also some shows about Punch, as well as Science Through Shadows, which Doug Duncan and I will be working on, which is about eclipses and occultations. Also, Monday morning, 6:33, Artemis 1 is launching. Yes, we have a camera on the launch pad and are doing a live stream in our dome. So come to Fisk at 6 o'clock and you can actually get as close to Artemis 1 as anybody in the world as it launches 200 feet from our camera. I also do occultation research, got to spend the summer in Australia doing occultations for the Lucy mission. There's my 2 seconds of fame after 100 hours of traveling. Tonight I'll actually be down in Larkspur doing an occultation of Didymos, which DART is going to be smashing into in a month. So using occultations to get much more precise astrometry for NASA missions that are flying to minor planets. Come to Fisk.
Thank you very much. Hi, my name is Dmitry Uzdensky. I'm a professor in the physics department and at the Center for Integrated Plasma Studies. And I do theoretical plasma astrophysics. I collaborate with Professor Mitch Bigelman and with Jason Dexter in this department and with Greg Werner in SIPS, as well as students and postdocs. And my interests lie in trying to understand fundamental plasma physical processes as they occur in extreme radiative and relativistic environments around high energy objects like neutron stars and black holes. Thank you.
Thank you. I'm Greg Werner, and I'm also in the Center for Integrated Plasma Studies. I work with Dmitry and Mitch Bigelman. And I have a sledgehammer, which is the particle in cell computer simulation technique. And you've heard the expression using a sledgehammer to crush a peanut. Applying PIC codes to astrophysical systems is not like that. It's like using a sledgehammer to crush a mountain. So we're very interested in how plasma instabilities can develop in astrophysical systems, and in particular convert energy from one form to another, and eventually, and especially to radiation, which we can observe. So this picture shows a current sheet, which is unstable to 2 different instabilities, and they're competing non-linearly, and it's all very exciting. Thank you.
Hello, my name is Don Schmidt, and I'm a research faculty at Ceres, which is another one of the research institutes at CU. I have affiliations with NOAA and NSO. I'm an observer, I do solar physics, and I've kind of bounced around between research analysis type projects and some science operations and some hardware development. And so kind of the things on the left, on the right here just show general projects I've been working on. I'm mainly here because I have 4 years of graduate student funding and I need to find a graduate student. This is a Living with a Star project that was just funded. And the big concept here is that we're looking at very high resolution magnetograms of the sun and trying to understand how those magnetograms, when you drive MHD models using those magnetograms, what sort of structures you develop in the corona compared to these lower resolution models. So there's a medium resolution and a high resolution magnetogram up there. The analysis will be essentially making those magnetograms and running the MHD models. And on the bottom here is looking at current sheets and how the development of current sheets differ in the corona based on these magnetograms. And this likely has a lot of big implications for things like the coronal heating problem, as well as like this, the switchbacks we're seeing with Parker Solar Probe. So it should be exciting. Oh, this will be done. I'm looking for a student here. The PI on this grant is actually in San Diego, so you get some beach time too.
Hello, my name is Tyler McMahon.
Bracken. I'm a current PhD candidate in the physics department working with Andrew Hamilton. So when we're not discussing grand unified theories and things like that, I spend most of my time figuring out what happens inside of black holes. So this is a simulation of what it looks like just when you've dipped below the event horizon. Nothing really special happens there, but it turns out if you go farther into the inner horizon, things start to get catastrophic. So I studied the quantum effects, things like Hawking radiation, and what blows up there. I also have a passion for teaching. I work with CU Prime, and I quickly want to plug the Grand Canonical Ensemble, which is a group that I organize, and we are a musical ensemble of physicists and astrophysicists and the like. We have a concert at the Physical Planetarium at the end of the semester. So if you're interested in joining that, talk to me. I'd be happy to chat. Thanks.
Hello, I'm Doug Duncan. I came to this department 20 years ago, and that was just about the time that clickers and learning assistants and fat applets all began. And I thought it would be interesting and probably pretty important to see if those things work. So I do experiments on you, on faculty and students, to see which technology works, is worthwhile and which isn't. I have the first published paper on texting in students. I can tell you 75% of your students text, whether you notice it or not, and it's worth about half a grade. I'll also second, yeah, anybody wants to show that, get a copy from me, many people do. I'll second what John Keller says. We have a very nice NASA grant to produce short video features showing off what NASA is up to now and who can work at NASA and in space. And we're in over 250 planetariums worldwide. So if you think you enjoy communicating science to the public, talk to either John or me, and we'll put you on the project team, and you'll do it and get better at it. Thank you.
Hello, my name is Anna. I'm a current second year grad student here. I work with Jeremy Darling on observational cosmology. I look at data from Keck primarily, hydrogen and metal line absorption between us and distant quasars. The primary goal of my project is to develop methods to measure the cosmic acceleration directly, which is very exciting. I'm primarily interested in cosmology and galaxies, and I'm also involved with UCW, our workers union for grads, faculty, staff all across campus. So if you're interested in that or anything that I mentioned, let me know. Thanks.
Thank you. Hi, I'm Sebastian Pineda. I'm a research scientist over at LASP. I'm showing here the activity across low mass stars and brown dwarfs. That's what I'm really interested in. And across all these different kind of phenomena, I use observatories across X-rays to radio telescopes. Specifically, the sort of near term, I'm thinking a lot about stellar winds. On one end, started to dabble in simulations. I have a web program trying to look at the surfaces of very low mass stars into the brown dwarf regime. So that'll be really exciting. And I'm also doing a lot of work in the radio, trying to look for signatures of magnetic star-planet interactions. So I have a bunch of different programs, and I'm looking for a couple of students. So if you're interested in any of it, please come talk to me. Thank you.
Hi, I'm Dave Wilson. I work in Kevin Francis' group over at LASP, and I do UV, X-ray, optical if I have to, observations of stars, and turn them into spectral energy distributions like this one, which people can use to do models of planets or whatever they want to do. This is one of my least favorite star, TRAPPIST-1. Yeah, and I'm also interested in white dwarfs and white dwarf M dwarf binaries and looking at stellar winds and Lyman alpha lines, things like that. And I'm also running the stars and stellar seminar stream for LASP. So if anyone wants to give a talk over at LASP, please come and talk to me because I've let too many spaces open. Thank you.
Thank you.
Hello, everyone. My name is Leah Hankla. I'm also a grad student in the physics department, but I've worked with Mitch since my first year, as well as Dimitri, and now I'm working with Jason. I use a combination of big numerical simulations and my analytic models to look at accretion disks. Specifically, I've been looking at X-ray binaries a lot recently, and just trying to figure out like what does the inner accretion disk look like, and how do the plasma physics that happens there influence what we observe. That's it.
Hi, everyone. I'm Peter. I'm a second year grad student. So I work with David Malaspina over at LASP. And I have a couple of projects. Primary one is using data from Parker Solar Probe to measure kinetic alphane waves in solar wind and understand their role in the turbulent cascade of magnetized plasmas, if they behave as predicted by theory, and how they heat and accelerate particles. And then I'm also working to develop a plasma sounder, which will be an instrument on board sounding rocket with a suite of instruments geared towards measuring small scale structure and joule heating in the aurora. So that will launch from Sweden in winter 24-25. So yeah, that's a little bit about me.
You're worried? Oh, okay. Okay. Hi, I'm Erica Nelson. I am an assistant professor here. I started during the pandemic. It was exciting. My entire world now is James Webb. I'm very excited about it. We started getting data about a month ago, and since have been working essentially nonstop. This is the thing I'm most excited about right now, these galaxies that are completely invisible in Hubble images and pop out in James Webb images. They look like these red ultra flattened objects or UFOs. Yeah, it was between that and Chonky Boys, so we decided this was slightly more professional. But one of these, it turns out, is actually a really massive galaxy at very high redshift, which we've lovingly termed the universe breaker. So that's currently in the refereeing process at Nature, and hopefully will get accepted in the next week or two. But I love James Webb and everything related, so please come talk to me if you are interested.
Hello, hi everyone. I'm Zach Berta Thompson, an assistant professor in the department here. I stressed out a little bit about the rule of no words on the slides beside my name. So I am also very excited about JWST. Beautiful 6.5 meter telescope in space, working spectacularly. I don't have such beautiful images of galaxies because I study transiting exoplanets. So watching when a planet passes in front of its star and blocks a small fraction of that star's light. So you're seeing observations here of WASP 96b. These are part of the early release observations. There will be papers coming out on these soon. You probably saw a ratty spectrum of this in press release if you were following JWST very closely. So the observations here are, we pointed our telescope at a star and measured its brightness as a function of wavelength. And then on the x-axis is plotting the time in which the planet is orbiting around the star measured in days. And so you're seeing a little dip there. And these data are just sort of like spectacularly, gorgeously beautiful. So like Erica, a lot of my world right now is working very closely with JWST data. And we have lots of students and postdocs working on that right now too. So it's a very exciting time.
Sweet, I was last. Did you do it in the 10 minutes before colloquium? Yeah. Do you want to just come stay? Go for it.
Hi, I'm Kirk. I submitted, I guess, 9 minutes ago. And I work with Jason. We're characterizing the broadline region of quasars, specifically using gravity data, which is this cool interferometer on the ESO's very large telescopes. And we're looking at quasar 3C273, which was my picture, has a cool jet. That's it. Thanks.
Anyone coming to the front? I don't see anyone coming to the front expecting to do a slide, so I think we've done it. Thanks everyone for staying on time and introducing yourselves, and welcome. And is there anything else? Feel free to stay and mingle, sure. Yeah, or run off to a comms exam. All right, thanks everyone so much. Welcome back.